In this video, I want to show a small neural network I created in GeoGebra. Here we have the input space where we can move the dot representing the input. And here we have the output of this entire neural network. And we can see moving this dot here changes the input values. And those input values are sent forward into the first layer of the neural network. And there, looking at this neuron, we have two inputs. Those are the input dimensions times the weights. And there we have those input functions. Here we go. Okay, this one is from the first input dimension to the first neuron. And changing this weight changes this input function. And changing the other weight changes the other input function. And we can see changing the weight of the one doesn't change something about the other. And there's also this bias of this neuron. And those three values, the bias and the two inputs, they are summed up. And this sum is sent through an activation function. In this case, it's the hyperbolic tangent. And then it looks like this here. And from the side we can see that it's a scaled version of the hyperbolic tangent. Okay, so if we put one of these values to 0, we see, yeah, it's the hyperbolic tangent, and here this value changes the smoothness. So the hyperbolic tangent has on one side a value that's close to -1, and on the other side a value that's close to +1. And here this part in between, there could be a rough cut, or there could be a very smooth transition. And negative values change the function. They just flip it. And considering also this weight, so making it non-zero, there we can see that it turns the function we got. So for example, if we have one value that is the one weight is 3 times the other weight, then we can see that this zero crossing line has like a slope of 3. 1 to the right and 3 down, and we get here zero crossing again. We could make it with higher values, so this one could be 1 and the other could be 3. And there the zero crossing is on the same line, but the transition is not that smooth anymore. Now adding the bias, we can move the entire function. So here was the zero crossing line, and now we move it in a perpendicular direction by changing the bias. This is what happens in a single neuron. And we can also look at the other neuron. And there we choose the weights differently. And therefore we get a different function. Yeah, that one has a more smooth transition because those values are not as large as those two values. And there the transition is not so smooth. Now we saw that we can only make those shapes where one half is above zero and the other half is below zero. But to get a more complex function, we have to combine multiple neurons in a second layer, which is exactly what happens here. So here we can, for example, add up the two functions. Yeah, we add them up, and then we see that there's some part of this function, but also some part of that function that we have here a part above zero, and there it gets above zero again. There we can adjust those values to get different functions. And the bias helps us. It's like elevating the entire function a bit or lowering it. But not exactly, because here we can see if we have a lot of bias, then it's just a flat plane, because the sum is sent through the activation function. Okay, and we can also look at the other neuron of the second layer, and there we see that it has a different shape because we have different values here, which we can adjust as well. And now in the final neuron, we add those values up again and get a final function. And there we can again play around with the sliders and adjust the function to our needs. That's basically it. You can play around with it. I have a link in the description to this GeoGebra file, and I think it gives some more intuition about what happens in the individual neurons